Hey everyone, my name is Sahil. I'm an MCAT tutor here at Shemmassian Academic Consulting, and today we'll be going over a Chem passage, and I'll discuss some of the strategies you can use when encountering questions like these on the MCAT. So I've got the passage pulled up here in front of me, basically just going to read it out loud, think out loud, outline it a bit, and then we'll dive right into the questions. Just as a heads up, on test day, you want to be going at a pace of about 8 minutes per passage, but since I'm going to be thinking out loud and talking things through as I go through it, I won't be going at that pace. So just something to be mindful of when you're doing your own independent practice. Shoot for about 8 minutes per passage. All right, with that all out of the way, let's get to it. Most biochemical reactions depend on the pH value of the aqueous environment, and many are strongly favored to occur in an acidic environment. A non-invasive control of pH to tightly regulate such reactions with defined start and end points is a highly desirable feature in certain applications. Okay, pretty straightforward opening paragraph. Just seems like it's introducing us something to like or it's giving us some background information on whatever we're about to read. So I won't really dig too deep into this. I think the main thing here is they're just telling us that controlling pH can really help regulate a biochemical reaction. So that's basically exactly what I'm going to write down for my summary. So we'll put pH control, regulate reactions. All right, let's go on and move on to the next paragraph. Researchers report a novel optical approach to reversibly control a typical biochemical reaction by changing the pH and using acid phosphatase as a model enzyme. The reversible photoacid G acid functions as a proton donor, changing the pH rapidly and reversibly by using high-power UV LEDs as an illumination source in the experimental setup. The researchers found that the reaction can be tightly controlled by switching a light on and off, making the technology applicable to a wide range of other enzymatic reactions, thus enabling miniaturization and parallelization through non-invasive optical means. Figure 1 displays the structure of the G acid. All right, so it seems like now we're kind of getting into the meat of it. Here we're introduced to this photoacid, this G acid, and it's basically reacting with water. And it seems like there's some acid-base type chemistry going on here where we have a proton being donated to our water and we get this like deprotonated version of our G acid. So just to summarize this, I think I would just put, we get our photoacid, or actually we have our G acid plus water kind of leads to G acid deprotonation. And honestly, this figure 1 right here is a great summary it's like a great visual summary, I should say, of the paragraph that we were given. And then the paragraph gives us some more information, such as like using these UV LEDs and, how this is just a very tightly controlled kind of experiment here, setup that they're using. But we don't really need to include all of that. I think just kind of the main idea is just this reaction that they put here for us. So with that out of the way, let's go ahead and move on to the next paragraph. In order to use the photoacid in a wide range of biochemical applications, the researchers ensured that it met certain requirements such as solubility in water, low toxicity, and excitability with commonly available, inexpensive illumination sources such as LEDs. LEDs have several advantages compared to more conventional illumination sources. They are more efficient, have a long lifetime, a compact size, and high reliability. Here, it just really seems like they're just kind of expanding on that whole LED stuff they had mentioned in the previous paragraph. There's an importance of the use of the photoacid with some more common, like conventional light sources. It doesn't really seem like we're getting too much related to like the experiment like itself and outcomes that were occurring there, but more so the importance of certain components of the model or whatever that they were kind of creating here, this approach that they had. I think I would just summarize this pretty much just like talk about the photoacid use with common light or illumination sources, and then they gave us, they talked about LEDs here, so I'm going to include that in parentheses as well. So in case you can't read it, I basically just wrote photoacid used with common light sources, parentheses, example, LEDs. All right, let's go ahead and move on to the next paragraph. The researchers chose an acid phosphatase as a model enzyme to further study the system. The activity optimum of APs typically lies at an acidic pH of 4.5 to 5.5. APs non-specifically catalyze the hydrolysis of monoesters to produce inorganic phosphate under acidic conditions. In experiment A, researchers used the acid phosphatase from potato, parentheses, EC 3.1.3.2, close parentheses, which is active between pH 4 to 7, with an activity optimum at a pH of 5 to 5.3. At an alkaline pH of 8, the activity of EC 3.1.3.2 is several orders of magnitude lower. All right, so there's a lot of numbers they threw at us and some pretty useful information. I think the most important part was just the pHs that they gave us. I know that's really relevant, especially with the content review I've done. So I want to really take note of that. So if I had to summarize, I would probably just write this APs, right? These acid phosphatases that we kind of talked about here, and put pH and mention that 4 to 7, they're active. But 5 to 5.3, which was mentioned right here, is optimal. And then we had about pH of 8 is going to be decrease activity. I think that's going to be what's kind of the key part of all this. And just kind of summarizing that and into kind of a shorthand here will make it easier if I need to refer back to these pH ranges instead of having to dig through the paragraph for these specific ranges. Just having them now listed out will make them a lot quicker and easier to reference. All right, I think we're down to our final paragraph now. So to assay EC 3.1.3.2, that's starting to become quite a mouthful, but activity, researchers use p-nitrophenol phosphate, parentheses PNPP, close parentheses, assay. So the PNPP assay is a colorimetric assay in which the substrate PNPP is hydrolyzed by acid phosphatase into the product p-nitrophenol. So you have parentheses PNP plus this inorganic phosphate in purified HPLC grade water as shown in figure 2. Alrighty, this is honestly a really nice and concise paragraph here, especially because we have just the reaction scheme, and if I'm being honest, I think that's actually the best summary of our paragraphs. So I think what I would just write is just PNPP colorimetric assay, and then I'll make sure when I look at my outline that I take a look at figure 2, since that kind of sums it up really nicely for us, where we have PNPP, p-nitrophenol phosphate, and using acid phosphatase, we get the p-nitrophenol and then that inorganic phosphate. So once we've outlined our passage, finished reading through it, let's go ahead and just dive into the questions. All right, so question 1, which of the following best describes the role of water in the deprotonation of the G acid? A, acid, B, catalyst, C, base, or D, aprotic solvent? All right, so for this, I say we look at that first figure that we were given. Let's see, where was it at? Right here. And this is where they talk about that G acid, and now they're asking us what's the role of water in this deprotonation. Well, if we see, what's happening is that we have this alcohol group, and the hydrogen is being donated to this water, so we get this H3O+. So essentially, the G acid is donating a hydrogen. And if we look at our option choices, we can think of it as G acid is donating hydrogen, but this asks us from the perspective of water, so the water is accepting a hydrogen. Therefore, it's not an acid because the acid is a G acid. The donation of the hydrogen is going to be something that the acid does. On the flip side, considering the fact that it's accepting a proton, that means it's going to be a base. So C to me looks like the best answer. But let's go ahead and eliminate the other two. Catalyst, the reason why H2O wouldn't really be a catalyst here is because we see in the reaction it's consumed and it's not like being regenerated, and we don't really have any discussion about like it's speeding up the reaction or lowering the activation energy. The H2O is very involved with the actual reaction itself as a substrate and as a reactant here. So I'm not really thinking it's catalyst. And then D, aprotic solvent. It's important to know your terminology here. What is protic versus aprotic? In simple terms, protic solvents, they can hydrogen bond, whereas aprotic solvents can't. And it should almost be glaringly obvious why this should be incorrect, because H2O is very well known for its ability to hydrogen bond. So definitely not aprotic. H2O would be protic. So we would go ahead and eliminate D, and C remains as our best answer. Alrighty, question 2. The researchers measure the energy of a photon during an experimental trial to be 3.3 times 10 to the negative 12 joules, which is the frequency of the wave. And then in parentheses, they give us Planck's constant, which is 6.6 times 10 to the negative 34. So when I'm given like data like this, or I'm just given some numbers, I like to kind of just list out what are the variables that I know and see which equation does this like all match up with. So I'm given energy, right? And they tell me right here, it's 3.3 times 10 to the negative 12 joules. I'm also given Planck's constant, which is 6.6 times 10 to the negative 34. And what I need to find is frequency. Well, I can instantly recall there is an equation that relates these three variables, and it's E equals HF. You might have seen it as something more like this. You might use this as your variable for frequency, or you might just use F. Both you'll see in your MCAT review books or chemistry, physics textbooks and whatnot, but I'm just gonna go ahead and write it down as E equals HF. So if I need to find frequency, I need to rearrange this equation to solve for frequency. So that would be F equals E divided by H. And so from here, it's just pretty much plug and chug. So F is going to be energy, which we had as 3.3 times 10 to the negative 12 joules divided by 6.6 times 10 to the negative 34. Alrighty, so to save time, one thing you should recognize is that for all of these answer choices, the exponents are like the same. It's all 10 to the 22. So we don't actually really have to worry about this part of our math. We can just do 3.3 divided by 6.6, and that's going to be 0.5. So once you have that, you could actually just go ahead and go with D and move on. Time is of the essence on the MCAT, so whatever little shortcuts you can take them. It's going to all add up in the end, and you'll definitely be more efficient with your time if you go that route. But if you still have maybe, let's say, some extra time and you really just want to double check your math, it's pretty simple. After you do 3.3 divided by 6.6, for dividing with scientific notation, you would just do negative 12 minus negative 34. So negative 12 minus negative 34, so that's basically negative 12 plus 34, which is going to be equal to positive 22. So that's how we get our positive 22 in the exponent, making D the best answer. All right, question 3. Which of the following functional groups is not found on the protonated G acid? They give us alcohol, benzene, sulfonate, sulfite. All right, well, if we scroll up to our figure here, immediately I do see my alcohol right here. So I see an alcohol, so we'll go ahead and eliminate that. And remember, they're talking about the protonated form, so we want to be looking at this side because this is the deprotonated form. So if you were focusing here, you might be thinking, well, there's no alcohol, so you might have went with option A. But you got to just be mindful. You got to make sure you don't make these types of silly mistakes where you overlook a key detail in the question. So they're saying the protonated form, so we want to be focusing on the reactant here. So on the left side of the equation, so we have our alcohol, so that's present. They also mentioned benzene, and I see the benzene rings kind of right there. So those are good. I'd eliminate that answer choice. The next one being sulfonate. Sulfonate looks a little something like this. If I can draw it out, sulfonate is RS. So basically something like that, where you basically have an R group, which could be pretty much anything, and then you have sulfur and then 3 oxygens. And then the sulfite is this right here. So you have a sulfur with 2 single bonds, each to 1 oxygen, and then like a double bond to an oxygen. Its formula would be like SO3 2 minus. So we got to see which one of these are not present in our figure up here in the deprotonated form of G acid. So right here and right here, I see sulfonate. But remember that sulfonite, which again was SO3 2 minus, which looks something like this, that I'm not seeing anywhere in that deprotonated form. So to me, the best answer is going to be sulfite. D, sulfite is going to be our best answer. Sulfonate, benzene, alcohol, all of those were present, but sulfite was not. All right, and let's get to our final question here. Researchers are likely to observe which of the following during a PNPP assay for EC 3.1.3.2 when pH is lowered to 5. A, cleavage of EC 3.1.3.2, B, an increase in inorganic phosphate levels, C, a decrease in sulfonate levels, or D, a decrease in EC 3.1.3.2 activity. All right, so let's think about this logically. First thing we should recognize, what did they tell us? They told us that the pH is lower to 5. Was there anything significant in the passage about pH values? Yes, the passage kind of opens with pH being really important, but then specifically in one of these final paragraphs, I think maybe the last or second to last, they gave us like specific pH ranges that we had in our outline. So we had put that this acid phosphatase, right? They usually have some sort of optimal activity in the 4.5 to 5.5, and they specifically tell us for the acid phosphatase from potato, which is EC 3.1.3.2, it has an activity optimum at a pH of 5 to 5.3. So right there, which we had written in our outline. So that means what's happened here is that we've lowered the pH to the optimal activity, to the pH which allows the optimal activity. So if we have optimal activity occurring, then most likely that means the reaction activity is going to be, there's going to be more activity. So right off the bat, we can go ahead and just eliminate D, because there wouldn't be a decrease in the activity because we're now at the optimal pH for the activity of EC 3.1.3.2. All right, well, if we have that, then if we look at our figure 2, which outlines the reaction scheme here, well, if we have an increase in the activity, right, if the activity is going to go up, then that means the reaction is going to be, we're going to push more to the right. So we should have more of this inorganic phosphate. And if we look at our answer choices, B says exactly that. There is an increase in inorganic phosphate levels. So I'm really liking B, and I think that's going to be our right answer. But let's go ahead and check out A and C as well. So with A, they mentioned cleavage of EC 3.1.3.2. Nothing in the passage really indicated that the enzyme itself would be cleaved. This really has more to do with the substrates themselves, that we're going to see this reaction here with the PNPP. We're going to have some hydrolysis, and we'll have the inorganic phosphate and then also the P-nitrophenol on the product side. So not really seeing any reason to believe that our enzyme is going to get cleaved. So I would eliminate A. And if we look at C, which says a decrease in sulfonate levels, sulfonate, there wasn't really anything about sulfonate being involved here at all with our EC 3.1.3.2 activity. So don't really see what's kind of the relevance here. sulfonate. So I would eliminate C. And actually go ahead and go with B. So basically, keep this one simple. You really just have to refer back to figure 2 and just see that, okay, well, if we have a pH of 5, well, they told us that's going to be the optimal pH, right here. And if we're at that optimal pH, this reaction should be shifting right, or at least we should have an increase in activity. And if there's more activity occurring, that means this reaction is occurring more, and therefore we should have more of this inorganic phosphate. Really simple. Everything else doesn't really fit and everything else just really isn't the most straightforward and concise prediction to be made here. You're most likely to at least observe that inorganic phosphate level goes up. Everything else here is kind of a little bit out of scope, or just don't have as solid reasoning as you do for option choice B. All right, well, that should wrap this up for this passage here. If you found this video helpful, please give it a like, subscribe to stay up to date with our latest videos, and check out the link in the description below to sign up for a free MCAT question of the day, where you'll get a free MCAT question sent to your email every single day. All right, everyone, best of luck with your MCAT studying.